We started this course with talking about specifications of an amplifier, and this was for our antenna amplifier. And we have seen that we had functional specifications, tells what function should the thing do, performance specification, with what level of quality should this function be performed, environmental or operating conditions, under what conditions should this function be executed, and are these specifications valid, and cost factors, what is the price we are willing to pay for performing these functions. And you can talk about operating cost factors, which is then power consumption, for example, but you can also talk about design cost factors, which is design time. We just focused on operating conditions. So we made a object performance specification and an object test specification. And one of the, so we started with an application description, and that was a lot of, let's say, text and some numbers, and we had to convert those in an object performance specification. And I renamed it a little bit because then I'm able to use later on the other symbols again. So F was used for frequency in MATLAB, so I called functional specification, functional requirement FR, and environmental condition EC, and cost factor CF. So this is only done in the last file. So here you see descriptions, values, and units, and how it should be tested. Now, what I did in the past 2 days was I made a SlideCap design in SlideCap, and I coupled all those specifications and all the performance aspects in SlideCap to this performance specifications. So if I change in the performance specification a number, I can redo the design, click on execute in MATLAB, and there will be another antenna amplifier, for example, for another antenna length. So that was the first thing we did. So then the next thing was design a negative feedback amplifier configuration based on the way the electrical quantity at best represents the source signal and the load signal. So which electrical quantity should be taken at the input of the amplifier, voltage or current, and which electrical quantity should be taken at the output of the amplifier, voltage or current. And we have seen that since the antenna, the impedance of the antenna is just a linear capacitor over a wide frequency range, and there is no uncertainty at all about its value, it does not add any uncertainty to the information if we take the short circuit current of the antenna rather than the open circuit voltage. Initially, we knew that the open circuit voltage was a measure for the electrical field strength in which we had our information. But since the antenna is linear and very predictable, we can also take the current. At the output of our amplifier, there was a long cable. And this cable should be driven from its characteristic impedance. And in this case, it was specified like 50 ohm. So we have two options at this stage. We can make something that converts a voltage into something that drives the cable with 50 ohm. And then we can decide which transmission 1 matrix parameters should be fixed of such amplifier configurations. So, and that's what we did in the configuration comparison. Well, let me first go to the table of contents. Here are a lot of configurations, and here in this one I select one of those configurations. Now let's go to this. So I have a configuration, for example, let's make it a little bit smaller so it fits on the screen, that uses voltage as an input. You see the source impedance is not drawn because this is only a test circuit for A, B, C, or D, in this case A. So voltage at the input, and the output, it has a characteristic output impedance of 50 ohm. It is realized by making both parallel feedback at the output and series feedback at the output. Series feedback, we measure the current, convert it into a voltage, and here the voltage is compared at the input. So we have voltage to current, voltage to voltage and voltage to current conversion of this amplifier, which means it is voltage in and a characteristic output impedance. So this is the measurement setup for A. This is the measurement setup for B, because the impedance, the output impedance, was set by A and B. And here we have the transmission parameters that we can calculate, and the output impedance is R times the ratio, the turns ratio of the transformers. Here we have another configuration, a configuration in which we use passive feedback. So we have a voltage divider here that divides the output voltage, and we make the output impedance just by connecting a resistor in source with a with the output. I see a question on the chat. Let me come to that question after this comparison stuff. So here we have a voltage attenuator. We compare it with the input. So this is basically a voltage passive feedback voltage amplifier, and we created the output impedance by means of a brute force technique, just placing 50 ohm in series. This is the measurement setup for A, and this would then be the measurement setup for B. You measure the short circuit current while driving it with a voltage. And here you have the transmission parameters, and from this you can design the values of the capacitors, and RO, of course, will be 50 ohm. Another one is one that uses the current of the antenna and converts it into a voltage. But now the antenna, the voltage to current conversion of the antenna is a differentiating characteristic, because the antenna impedance is capacitive. So we need to have an integrating amplifier to obtain a frequency independent output. Now here you see this is a trans impedance amplifier. So this fixes C, and here this one fixes D. We measure the current through the and convert it again into a voltage. This voltage is buffered and then driven by the capacitor again and subtracted here. So if you calculate A and B and C and D from this configuration, you get this, and you find the output impedance and the trans impedance of this configuration. So this is a simple one again, in which we also sense the current of the antenna and make an integrator, and here a brute force technique for the output impedance. So this is basically the generation phase. So here you see the thing, and now it comes to the comparison of the solutions. So I have, let's say, this for configurations. This was non-energic, this was non-energic, this was passive with brute force, and this also passive with brute force. And now let's say we just say, well, as soon as it is non-energic, it gets a plus for power, or it's better for power and for noise. This one was also non-energic, but there were more passive sense elements in it. So it's a little bit worse than this one. Frequency response. There's not much of a difference between the two things, but here is a big difference, ESD and nonlinearity. Remember, there was a requirement for the amplifier that it should have ESD protection at the input. Now see what happens if I would make an amplifier with a voltage input. So the first one was an amplifier with a voltage input. And of course, there will be here the source capacitance. And here then should be an ESD device to protect the input against high voltage discharge. But the ESD device is not simply an on and off device. Even under very small signal conditions, you will find that it creates some parasitic impedance here in parallel with the signal path. And this is a strong nonlinear element, which means that there's a lot of distortion from this voltage, if you would have the capacitor here, to the input voltage of the amplifier. And this distortion cannot be eliminated with negative feedback because it happens before the signal is in the amplifier. Now let's go to a version in which we use the current. And for example, this simple one. If we use the current, so here is the antenna capacitance in parallel with the source, of course, and then you could say here we have our ESD device, but now it is at the input of the controller, and the input of the controller has zero input voltage if the loop gain is very high. So it means that any nonlinear parasitic impedance here will not do anything with the distortion as long as the loop gain is large enough. It can be killed with loop gain. And that's a huge advantage of this configuration. So that's why you find in ESD here the pluses for the topologies that have current input. So then if there's some non-energic feedback and there's transformers, we say it's very complex and you cannot easily find transformers for such a wide frequency range. And here we total up and we have a few options. And we will select for this course this option, the last one in the table, which is basically this option. And of course, it's a voltage source in series with the capacitor there. So that is the thing we are going to make. But first we generate a number of solutions, then we do the comparison, and then we select. So here's what we do. And now we have to find all kind of showstopper values for the controller that we put in, because the feedback elements are known. We know the antenna impedance, we know the amount of amplification that we need. So we know the value of the feedback capacitor, we know the value of the output resistor. There's not much to design there. So now we are going to focus on the controller. But the next thing we need to do is find showstopper values for the equivalent input noise sources of the controller. Now let me tell you something. Let me first go through this list and let me tell you why this list has this order, because I can just go through them point by point, but then why do I first this point and then another point, and why don't I swap the order? We are going to use negative feedback, and we have seen that negative feedback is an error reduction technique, and we are capable of reducing errors. And what kind of errors can we reduce with negative feedback? Well, weak nonlinearity, for example, in the controller can be reduced by negative feedback by increasing the loop gain. The bandwidth, so bandwidth limitation, can be, let's say the bandwidth can be increased. The limitation can be decreased, so the bandwidth can be increased by increasing the loop gain pulse product, as we have seen. So for bandwidth and for nonlinearity, if we have not enough, we can simply make more loop gain pulse product and cure our amplifier. But there are a few things that cannot be cured by negative feedback. For example, clipping of the output, the voltage and current drive capability. Well, if the amplifier clips, it has no gain anymore, so the loop gain is zero. So basically, loop gain can do nothing. So the voltage and current drive capability of an amplifier are basically equal to those of the controller, or even worse. Noise, equivalent noise sources of the feedback amplifier can at best be equal to those of the controllers. In those cases, we speak of non-energic feedback. But in most cases, the feedback networks add noise and enlarge the contribution of the noise sources of the controller. So we have to start with noise because we have no measure to do anything with that. We have to start with voltage and current drive capability. These are requirements that directly follow from the specification, and we cannot do anything with negative feedback. Now you would say, well, bandwidth also directly starts from spec. Yes, but if we cannot find a controller with enough bandwidth, we can put two controllers in the loop. just make more loop gain pulse product. And this doesn't work for gain or voltage and current drive capability. And there's another thing. Biasing, that's why we are going to focus on a bias solution, on a high-level bias solution. Since we're not going to make all kind of current sources to bias the devices, because that is not relevant at this stage. We are just working with operational amplifiers. But we must have a biasing solution, because that sets the voltage and current range that can be delivered by the amplifier. And it will tell us about biasing errors that remain after, let's say, we need some input current in a terminal of an op-amp. We have some resistor that gives voltage drop, etc. Those kind of errors we need to know, because it's just like noise. We cannot reduce them with negative feedback. So that's why here you find first noise sources of the controller, then a high-level bias solution, and in this bias solution, I talk about also voltage and current drive capability. And then we are going to bandwidth. Why to bandwidth and not to nonlinearity? Well, we are not dealing with nonlinearity here in this op-amp course, but later on. We must first have a stable system before we can study its nonlinearity. And before we have a stable system, we must have a system that has enough bandwidth. So we start with bandwidth, then frequency compensation to make it stable. And if the amplifier is stable and has enough bandwidth, then it is worth a while to look at a weak nonlinearity. But this is not what we are going to do in this course. In this course, we are going to select an operational amplifier. So we need to talk about that. So after we found all kind of showstopper values for all kind of elements, we are going to select the operational amplifier, and then, of course, we need to check if everything works as intended. So we are making a model of it. And for the analysis of the small signal behavior, we make a small signal model for slide cap, and I'll have a model for the voltage gain and the output impedance, and then we can check the stability. We need a good model that has an appropriate, accurate description of the small signal behavior, and then we can evaluate the stability and apply frequency compensation if necessary. Now, what I did not do was put a complete macro model in SPICE, or we have all kind of behavioral models here. I just went to step 10, build it and test it, and I will show you the results later. So let's go again through the whole storyline here, and the configurations we did, and now we need to find the showstopper value for noise of the controller. So here is the script. I put everywhere the script, but maybe it's better just to go to the noise budgets. The model that I use for evaluation of the noise is like this. I consider all other performance aspects of the operational amplifier of the controller as ideal. So basically, we call this, you could call this a noisy nuller. It's a nuller with its two equivalent input noise sources, and I have given them unknown values for the spectra as I and as V. This is the amplifier, voltage of the antenna capacitance, and this is the feedback capacitor. Then we have this output resistor and this load, of which I have modeled the noise accordingly, just as current sources in parallel. And what I then do is I calculate the noise, the source referred noise there, because I have a spec for the source referred noise, and try to find budgets for SI and SV. That's what we are doing. So you see, everything is defined up this level, except for SV and SI. We know the load, we know the output resistor, this is temperature, you can change it, this is Boltzmann constant, and this is the antenna capacitance, and this is the feedback capacitance. We need to have a gain of 2, so this is half the value of this one. Main index, noise budget, sorry, noise budgets. So we can calculate with SlideCap, and some of you did already, so I hope this is clear, but it's in the script. I can go to the script later on if you want. The total source referred noise in volts squared per hertz. This is in volts. If I don't say it differently here, we have it in volt per square of hertz, but then I write it explicitly here. So this is volt squared per hertz. Then you see that we have this is the spectrum of the voltage noise source of the op-amp, and this is the spectrum of the current noise source of the op-amp. So here we have a contribution that increases for decreasing frequency. We have a kind of basic level, and we have a kind of level that depends on the voltage source, the voltage noise of the op-amp. Now remember, we had specifications that were given as a floor noise. You could say for very high frequencies where this one doesn't contribute anymore, we can solve as V. And for very low frequencies where this dominates, we can solve as I. So that's what we do. We find the showstopper for SV, the maximum value that it can have, if we set all the other noise contributions to 0, except what you cannot put to 0, and that is the resistors are in there. So here we have SI, we put Fi to 0 and solve SV, and then you need an op-amp of 3.3 with 3.3 nanovolt per square of hertz or less to comply with the specifications. The showstopper value for SI is found, but you see, then we must look at a very low frequency where this dominates, and we set SV to 0, and then we can solve the spec of the 1 over F noise, and we have a spec, for example, at 100 kilohertz, and then we find 40 femtoamps per square of hertz for the maximum noise. And the script, of course, is in it here. So you see here, I link to the specs. Here, I calculate with the antenna model, the antenna capacitance. I define the feedback capacitance from the gain specification and the specification of the output resistor and the load resistor. And then I define these parameters in the circuit. RO was also from the specs, RL was from the specs, and then you can do parameters to HTML. And if you do that, you find them here all calculated. But if I change the spec, this will change. So if I change the length of the antenna, CF will change. And the whole noise calculation will change. I will show you later on. That's the noise budgets. And let's go back to here. Then we have determination of the budget. Well, then I do it numeric. Although I still have two symbolic variables in it, I can do this. I can solve this numeric means that it substitutes all the numeric values of the components that it has already and leaves the other one symbolic. So noise, source, and detector, and then I get the source noise by get I noise from the execution result. That's all. Then I define some symbolic variables that I need, and I put this source referred noise on the page, and you have seen it. And now the maximum value, and here VPA means variable precision arithmetic. That is to get a numeric value from something that is calculated by the symbolic toolbox. And here you see with the second argument is the number of digits that it will give you. And then this is important, solve. Substitute. So I'm going to substitute in this source noise spectrum the value that I want as a floor. So I'm substituting I'm subtracting first the value that I want. I'm solving this for SI, sorry, for SV, and I set SI and F SI to 0 and F to the maximum frequency of interest. I could have said here, because there's no argument for solve, I could have put here, comma, SV, so that the program knows I'm going to solve SV, but there's no other variable left as SI, F, and SV. So if I substitute this one, there's only SV left. So that wasn't necessary. And then you have, I find this SV max and I put it on the page, and that's what you saw. SV max is here automatically calculated. So if the specs change, then the budget for this one changes. And similar way, you do this for SI, and you find this 40 femtoamps per square of hertz. Let's go back to the next step. I have to go back a lot. Where did I come from here? Okay. Design a high-level bias solution. Find showstopper values for static, dynamic, voltage, and current drive capability. Those were already in the specifications. I already have in the specification the peak-to-peak output voltage, the peak-to-peak load current, and the slew rate at the voltage slew rate at the output. So I'm not going to do that. The equivalent input offset and bias quantities, I didn't do that because for this specific example, it is not that much of interest. So it will be a lot of work, but it doesn't give you much. Let's go to the biasing. Oh, better go to the slide cap output and the biasing concept. The biasing concept is like this. We want to have, of course, this is still a nuller, but we will know it will be a controller. And if we supply it between, for example, 0 and 5 volts, then the output cannot swing below 0 and above 5. So let's say if we would have 5 volt, then you would like to have this operating point here at 2.5 volt. And that's what you do by lifting up this pin to 2.5 volts. So that is VB. So basically, in this case, you find VB at the output, and this DC current path provides it. It makes DC feedback, so that this will also be for DC 0 volt and no current. And in practice, of course, there will be a controller here, there will be an op-amp here that needs a very small current, and that sets a limit to RB because any current here will make an error. Now, since I know for this exercise, but I didn't discuss this with you, I know for this exercise we need a operational amplifier with a very low noise current, equivalent input noise current. It will also need a very low input noise bias current because the input noise current is associated with the input noise bias, with the input bias current. So we forget for the moment about any voltage drop, but of course we could make an, as I have done in this chapter 5, I think, in the biasing example, we could make budgets for it. And then, of course, this point is now 2.5 volt, but we want to have 0 volt here at the cable. And so we put a capacitor here to block for DC. We have to calculate this value, and we have to calculate this value. This does something with the noise. It generates noise, but also it establishes a high pass filter from here to here. And this capacitor establishes a high pass filter from here to here. So as soon as I present this biasing scheme, I want to have values for showstopper values for RB and CC. And that is what we are going to do in this thing. So, and I've written some text. So these are the three components, VB, RB, and CC. VB, well, probably you want to put it in the middle, half the supply voltage. And that's all for the moment, because I don't know yet what will be the supply voltage. I need to have an op-amp first. RB, establish a high pass corrector. And so the time constant is in the script, and from this you find a minimum value of 500 kilo ohm. So this is about 500 kilo ohm, which means if you make this smaller than 500 kilo ohm, you won't get your 100 kilohertz as low at low frequencies cut off. You need it at 100 kilohertz. This is the same for CC. The minimum value to get your high pass at 100 kilohertz, that was the specification, is 16 nanofarad. So this is what is calculated here, and it is done in the script. Bias concept M. You can see the script here. Here I just put the formula in it. Of course, you could do a symbolic simulation there, do voltage to and generate this formula with the slide cap itself. I didn't do it. I know it's just connected to the schematic that I have and calculated in this way the minimum values. And so for the noise, and then it selects. I calculate the minimum value for cutoff frequency, I calculate it for the noise, and it takes the maximum value of the two values that I find, and it should not be smaller than that. And in this case, it will turn out that the noise is decisive over the value that we want. So that's what you find here. Sorry, bias concept. At the end, it calculates 500 kilo ohms for high pass cutoff. It calculates 10 mega ohm for current noise, and it selects the largest one from this and automatically, and it's in this case 10 kilo ohms. So if you change the spec and current noise can be much larger, then it ends here. Or if you change the spec to 10 hertz, then maybe this one becomes dominant over the current noise, and then it will select the other one. And in the same way, it calculates a capacitor. Okay, that is the biasing. For the VI drive budgets, sorry, that's the next step, that is here. I didn't do much because they were just in the specification already, so I didn't do much. You will find them later on in the table. So then we are coming to the gain bandwidth product of the operational amplifier, and maybe interaction with other elements that cause bandwidth limitations, such as the output impedance of the device and the input capacitances of the device. So let's see what we can do there. Oh, I click to the script because the problem with I make all these web pages with Sphinx. Sorry, and Sphinx is not able to work with spaces in file names. So, oh, I was a little bit going back. So if you see in the output here, if you look to the files in MATLAB, some file names have spaces, and I cannot link to them. So I can only link to file names that have no spaces automatically. So let's do the gain bandwidth product. What kind of circuit do I need there to evaluate what I need? So I made a voltage controlled voltage source. I gave it an output resistance, and I gave it an input capacitance. That is basically a simple model of an operational amplifier. And I realized the following. This input capacitance for the loop gain reduces the loop gain. So if the input capacitance gets about the same value of the antenna capacitance, then the loop gain roughly is half as large as it could be if it were not there. So this has a large influence on the requirement for the gain bandwidth product for the op-amp. The output resistance maybe also, but let's study here. We have here 50 ohm and 50 ohm, and here we have something like 3 PF. So 3 PF and 100 ohm, if the output resistance of the operational amplifier were infinite, then the pole that it let's say if it is 0, it doesn't create a copole because I have a loop of capacitors and voltage sources if this is 0. So if it is finite and it has the largest possible value, let it be much larger than 100 ohm, then the pole stays at about 100 ohm, and this capacitor, which is 3pf, and 100, which is 300 picoseconds, which is 500 megahertz. So whatever this RO will be, it will never cause a pole in a dominant group. It will always be a non-dominant pole on this ground. So that is important to realize. So I use this model, but basically we are only going to work with RO equals 0, because whatever I put in it, it will never have a dominant pole. And I want to have the loop gain pulse product of the dominant poles only. That is easy to calculate symbolically. So here it is done. I calculate the gain bandwidth product requirements with RO equals 0, and you find indeed that there is a minimum. I need 90 megahertz. Well, if this is 0, I need 90 megahertz in this one. Well, this is attenuation of 3. I want to have 30 megahertz, so in total I need 90 megahertz. That's easy to see from the schematic. And here, if there's additional input capacitance, I need more. So, and here's the description that I told you, that RO will never cause an extra dominant pole. So I can just leave it out of my estimation all the time. So I now have a requirement for the gain bandwidth product together with an input capacitance, and later on I can just fill in a value of the input capacitance that I think that is reasonable for these types of operational amplifier, and see what I need together with that. So I have a requirement for that. And now we have a very interesting thing, but I first want to go back to the thing. Search for an operational amplifier that can be used as a controller. The first thing I'm going to do is make an overview of all the requirements that I have now. Some requirements were in the specifications, and others, such as the noise of the operational amplifier and the gain bandwidth product, I have calculated here in a few files. So here you have a script, and what I'm going to do, here you see all kind of variables, the peak output voltage, the peak output current, the slew rate, the voltage slew rate, SV, the spectral density, voltage, spectral density, current, the input capacitance, the gain bandwidth product, CI, what the hell was CI? Oh, that is just a variable I need here from this one. Yeah. VP, the power supply voltage, the RB, the feedback resistor, CC, the coupling capacitor at the output. And you see either there are specs in, or there are values from things that I have calculated. And I write those things to opamp.csv, to a CSV file, to have a nice list on, and then I open the CSV file, put it on HTML. So this is basically programming and making a comma separated value, a specification file with numbers that are generated from the spec. Of course, you don't need to do that, but this is also to show you the power of SLICAP as report generator. If you make circuits that are alike, you know, if you make another antenna amplifier with a shorter antenna, then you just change one parameter, you run everything, and your report is up to date. So let's go for that page. Select components, and here you see the result. Nice requirement. This comes from the specifications directly. This comes directly from the specification. This also. This is what we calculated, 3 nanovolt per square of hertz. This is what we calculated, 40 femtoamps. This is just what I assume for input capacitance, but you can change this, or you can express the gain bandwidth product as a function of CI. Then you have 2 parameters in one thing. But you see, with 4PF, I need 127 megahertz gain bandwidth product. Bias resistance, this is that it makes all the current noise, so there's no budget left for the operational amplifier. And this is that it sets the low frequency exactly at 100 kilohertz. And if I run for another value of the antenna length or for another value of the noise spec, then all these things are updated automatically. And then we are going to select one, and I found one, and it is not even perfect because this operational amplifier, maybe I should go to the web and do for you ADA 4817. Four nanovolts squared of hertz and not 3, but you cannot get lower. You can get lower, you can get 3, but that is not a unity gain stable operational amplifier, and it will be hell to get it, and it is very high frequency. It will be hell to get it stable. So we see basically we had for this antenna length a showstopper for the noise, because we cannot find a controller like this. And of course, the solution would be then use, for example, a discrete FET in front of the operational amplifier that has a low noise voltage. But this is not to this course. This is nice to do in the next year. The current noise was allowed to be 40 femtoamps, but we have only, this one has only 2.5. So that is good. Input capacitance 4 PF, well, we have much less. You see, so this is like maximum bias current 2 picoamps, which would over your bias resistor of 10 mega ohm only give you like 2 microvolt offset. So that is 20 microvolt offset, sorry. So that is also not really much. So this operational amplifier is what I'm going to use. And in the data sheet, you find some specifications. And of course, those specifications are far from complete. For example, a lot about some fixed gains, but we want to use it in our own way. And we need just the gain bandwidth product. Here you see the output impedance, but what they don't tell you is that is what they call the closed loop output impedance. So it's the output impedance of a follower that's below 0.1 ohm, and it goes up to 50 there. Here you have the gain and the phase characteristic of the operational amplifier. And so we have to map that on a slide cap model, and that's what I'm going to do in the next session. Here I have a model in a library. Believe me, it took me some time to fit it, and I don't expect you from you to fit it as accurate as I did. It's not even necessary, probably, because we don't use it for very high frequencies. And this is the value of the output impedance, and this is the fit of the voltage gain. I will show you later on how it works, and then we can do the plots. Now, this is gain and phase, and this should map on this one. Well, you see, this looks quite unrealistic for me, but okay, it's what they say it is. This is also not exactly order 1 or order 2, it's something in between. But this is a nice fit. You see here also the influence of a 0. You see the phase going on like this. So this is really a very nice fit for this operational amplifier over a wide frequency range. And you see 0 dB is about 400 megahertz of this operational amplifier. Then we do the same for the output impedance. That is much more complicated because it's a so-called closed loop output impedance. And you see here the results of my fit. It's a little bit too large. It's 0.1 ohm here at 1 megahertz. It should be below, and it should be only 0.1 ohm at 2 megahertz. But 0.1 ohm and 100 ohm load is not really important. These peaks, there's only the first peak. So up to 1 gigahertz, it is reasonably modeled. Good enough for us. So, and then we can go to the next step, which is basically, well, if we selected the correct operational amplifier, it will provide us enough bandwidth so we can immediately go to frequency compensation. Let's go to frequency compensation, and here is now our complete amplifier with a bias resistor in it, but not the coupling capacitor here. I didn't do that. It's quite predictable what it will do. And so now we can only focus on this roll-off character. And I added a phantom zero resistance, although I set it to 0. This is a type of resistor that can have 0 value. Normal resistors in this resistor cannot have 0 value, but this one can. It is another library element in the LT-SPICE library for SliCap. But I put it to 0. Later on, you'll see we don't even need it. There's no frequency compensation needed for this amplifier. And then we can use it for bandwidth limitation, because the amplifier will have a bandwidth of approximately 100 megahertz and we need only 30. But that I don't want to discuss because it doesn't belong to this course. So let's do the asymptotic gain model and plot the gain and phase characteristic. And you see indeed here the loop gain passes the 0 dB here at about 100 megahertz. We needed 30, so this is good enough. And it's a first order roll off here. This is 40 dB and this is 2 decades. So this is first order roll off. You can also check this from the poles, and of course you find a few poles and zeros at very low frequencies because that is what the biasing element did. And here you see the root locus, so it is nicely moving. One pole is moving to the left, just like a first order system. So the amplifier does not need compensation. Here you see the operational amplifier. Here you see the coupling capacitor at the output. Here you see I did not take half of the power supply voltage. It had to do with the common mode input voltage range of the operational amplifier, but it can be changed. Here you see ESD protection. Here you see there was no phantom zero required. I put a little inductor in it to prevent very high frequency signals coming in. And together with the resistance of the source that I have, it was enough damping, but you can forget about this. Unfortunately, in the schematic, there's not 3.3 PF, there should be, because I changed it later, but I didn't change the schematic. And I used, instead of 10 mega ohm, 100 mega ohm as feedback resistor. And here you see how I dealt with the power supply. The power supply, there was 5 volts on the cable, 5 volts here. The low frequencies are passed through and generate the power supply. And here the high frequencies are passed through and give you the signal. On the other side is the same kind of circuit. But don't worry too much. You will use this with a separate power supply. Removing this all, just put your power here. Here you see the amplifier with the ESD protection. A very small device here, but another gas discharge tube here for sparks. Here you see the test fixture. I can put an antenna on it. I can put a signal on it to measure. And here is the power supply giving you the supply and taking also the signal from here. So this could be this very long cable, but for the test fixture, I just have a short one. Then here, this is measured with one analyzer, you see the low frequency cutoff. And with me, it is not at 100 kilohertz, but the resistor wasn't 10 meg, but 100 meg. So you see the cutoff is about at 10 kilohertz. High frequency roll off is about at 100 megahertz. as predicted by the model. This is a sine wave non-average, so you see some noise on the measurement results. And this is the response of a square wave, and you see there's a little bit overshoot. So this is not a MF, this is MFM, but it's higher order, and the reason is this inductor in front of the whole thing that creates it. Creates a little bit steeper roll off here to suppress for very high frequencies. So that's it.